we're going to discuss um, 8-bit addition, how to do 8-bit additions in 8086. Now we'll start. Okay. Okay. Thing here is program to add 8-bit numbers. So data segment, I hope you know, 8086 contain data segments as well as code segments. Data segment will hold the data and code segment will hold the instructions. Data segment will hold as well as a data segment. And these are all the code segments. These are all the code segments in 8086. This set of codes is used to terminate the program. Data segment will hold data, code segment will hold instructions. Okay, so we will need to begin with the data segment and end with data ends. Similarly, if you start code segment, you will need to end with code ends. And then start is the keyword which tell you that instruction will be start from that position. After writing all the instruction, it will need to end with end start. And then data segments we know very well. It will contain the data. So here I define two input variables A and B. These two are of 8-bit numbers. A, I assign it as a 10H. It is of 8-bit, and B with 10H. It is also 8-bit. So if you want to store a 8-bit number variable, we need a data byte. This will store 8-bit data. So A has 8-bit, so type here is data byte. B also contains 8-bit value 10, so it is of type data byte. Sum, if you add two 8-bit numbers, you will get 8-bit output. This one is constructed as a sum. A also a 8-bit number, B also a 8-bit number. After adding A with B, you will get sum as 8-bit, and there is a chance for carry. Now we will see how to add these two numbers, how to store the results in output variable sum and carry. So data segment begin with data segment and end with data ends. Code segment begin with the code segment and end with code ends. So inside the code segment, we will need to define the keyword called assume. Assume is the keyword simply used by assemblers to convert the instruction present inside code segment into a machine level code. So CS determines the code segments, DS determines the data segment. When you call CS, this will execute all the instruction present inside the code segment. So if you call data segment DS, this will help you to get all the data values from the data segment. Then start. It's the keyword used to start the instructions. First instruction is move AX comma data, move DX comma AX. This instruction will help you to get offset address of data segment by simply calling the data. This will go to the data segment and simply copies the offset address, that means memory locations available in the data segment, and this will be assigned to the AX register. This will simply copies the offset address of data segment to AX register and simply pointing out all the memory locations by simply giving move DS comma AX means this will point out all the offset address in the data segment. Offset address means this one. We have the data segment with the different memory locations with a different address 2000H, 2001, 2002, 2003, 2004. These are all the offset address. This one is base address. So AX is a register. This will be mainly used to point out the offset addresses because the data segment contain different address location. If you want to access a random address in the data segment by simply calling the AX register, we can able to access any of the variables or data stored inside the data segment. That thing will be done by AX. This instruction will store the offset address of DES, that is data segment. By making use of this instruction, we can able to access any of the values inside the data segment. Then this instruction is very important if you do 8-bit addition. Okay, just wait for a minute. I will check the recording. It is fine. First, we will see move AL, A. What this instruction will do, move AL, A. This will simply copies the value of A to the AL register. What is the value for A? 10H. Now the value for AL is 10H. This will simply copies the value for A into AL register. What is the next instruction? Add AL, B. Add AL, B. What this instruction will do, this will add the value for AL with B and store the result in AL register. What is the value for A? 10. What is the value for B? This is also 10. What is the binary equivalent for 10? 0, 0, 0, 1. 0, 0, 0, 0. But similarly for B, 10 is 0, 0, 0, 1. 0, 0, 0, 0. After performing add A, B, this will produce result as 0 plus 0, 0, 0 plus 0, 0, 0 plus 0, 0, 0 plus 0, 0, 1 plus 1, 0, carry 1, 1 plus 0, 1, 0, 0. What is the output for AL? So after adding AL with B, output will be stored in the AL register. What is the output? First group 4 bits, then group remaining 4 bits. Binary equivalent for 0, 0, 0 is 0, 0, 0, 1, 0 is 2, 0. If you add 10H with 10H, the sum will be 20H. This will be stored in AL register. What is the carry? Carry here is 0. There is no carry will be produced if you add these two different numbers. So see here, after adding AL, B, the output result is stored in the AL with value 20H. If you add 10 with 10. After that, jump. J stands for jump. N stands no carry. If there is no carry is produced, this will move to the skip subroutine. This will simply move to the skip subroutine without executing this instruction. Because carry here is 0, this jump instruction will simply move the instruction pointer to the skip. This will not execute this instruction. This will simply move to skip and execute this instruction. What is the instruction? Move sum, AL. What is value for AL? 20 will be moved to sum here. Now sum here is 20H. 20H. What is the carry? There is no carry is produced, so carry is 0, 0 as it is by default. Carry here is 0, 0 only because carry is not produced. So after that, move AH, 4CH, move AL, 0, 0, INT 21. This set of code will help you terminate the program, but simply just copy and paste it. This is a default code. Code in start. So after adding 10 with 10, what is the value we get while doing the manual calculation, 20H. Now we will check with the simulator what will be the output. Okay. I'm just assigning the value for A as 20H. Value for B also 20H. For 10H. 10H. What is the value we get while doing manual calculation? The output here is 20H, carry is 0. Now we will check with simulator what will be the sum, what will be the carry. A is 10, B is 10. Sum here is 20, carry here is 0. Check with PPT. Sum here is 20, carry here is 0. It validates the computation is correct. Next, we will see one more example with carry. Value for A here is 0FF, B here is 0FF. Don't say this one is 16-bit data. For example, value for here is FFH, B here is FFH. For example, if you define FF in 8086 simulator, this will be considered if you define A equal to FFH. Without giving 0 before this numbers, B equal to FFH. FFH without giving 0 value before the number. So with this will be while if you give A equal to FF, B equal to FF, 8086 simulator, this will be considered as a variable, not a value. So if you this will throw an error. So if you want to consider this as a number, you will need to prefix this number with the zeros. Then only this will be considered as a data. Otherwise, this will be considered as a variable by simply defining FF. So wherever you define the variable, input variable with the alphabet, simply prefix with the zeros. Then only this will be considered as a value. Otherwise, this will be considered as a variable. Keep in mind. So we have data segments and data ends, code segments. We have the code ends. This set of codes for terminating termination of programs. This is data segment code. We are assigning the value for A as FFH. Value for B here is FFH. Then sum I defined as a dummy value, carry with the zeros initially, and then code segment assume CS colon code, DS colon data. Okay, this is assembler code. This code is mainly used for calling code segments to fetch instructions. This is a data segment. Is mainly used to fetch data from data segment memory. Start. This keyword is mainly used to initialize defining the instructions. Move AX comma data, move DS comma AX. This will assign the offset address of data segment to AX register by simply access different address locations in data segment. AX hold the offset address of data segment. This will help you to access different locations in data segment to fetch different data from data segments. Then this instruction is very important, what I explained previously. First instruction is what? Move AL comma A. This will simply copies the value for A in the AL register. Now the value for A is FFH. H stands for hexadecimal. Next instruction is add AL comma B. Add AL comma B. Value for AL now here is, let's wait for a minute. Value for AL here is now FFH. Value for B here is also FFH. FFH. What is the binary equivalent for FF? F here is 15. 1, 1, 1, 1. Similarly for another F. 1, 1, 1, 1, 1. What is the value for B? Binary equivalent 1, 1, 1, 1. 1, 1, 1, 1. Add these two values. So you will get 1 plus 1, 0, carry 1. 1 plus 1 plus 1, sum 1, carry 1. 1 plus 1 plus 1, sum 1, carry 1. 1 plus 1 plus 1, sum 1, carry 1. 1 plus 1 plus 1, sum 1, carry 1. 1 plus 1 plus 1, sum 1, carry 1. 1 plus 1 plus 1, sum 1, carry 1. 1 plus 1 plus 1, sum 1. There is a presence of carry. Carry will be propagated. So this one is, there is a presence of carry here. Carry will be 1 here. So after adding this AL with BL, the result will be stored in the AL register. Then what is the next instruction? After AL comma BL, the result will be stored in AL register. Then jump, no carry, skip. So after adding AL with BL, there is a presence of carry. There is a carry. There is a presence of carry. If there is a carry, this instruction, jump instruction, will not work because there is a presence of carry. This instruction is jump with no carry. But after adding A with the B, you will get a carry. So this instruction will not execute. This will move to this instruction, increment carry. Initially, what is the value for carry here? 0 0. So if you add two different numbers, then if there is a presence of carry, means now the carry will be incremented. INC stands for increment. So now the carry will be incremented with the value 1. Then what is the instruction? Move sum comma AL. Move sum comma AL. This is the value AL. What is the binary equivalent for AL? This one. 1110 here is 14. That is E in hexadecimal. 1111 means 15. The hexadecimal equivalent here is F. Now AL here is FE. AL here is FE H. AL value here is FE H. If you execute this instruction, move sum comma AL, the value for AL will be moved to sum. Now the value for sum here is FE H. What is the carry? Carry will be 1. After that, this set of code is for termination. Code segment is ended. End the start segment. So now we will check the output after adding FF, two different 8-bit numbers. The sum here is FE, carry here is 1. We will check with the simulator. See here. It will close all the unwanted windows. After emulate, run, check for trace. After adding, so 10, 10, 20, carry 0. Now I change the value for A and B. A with value 0, FF. B with value FF. Check if I don't define 0 before the value. What is error? See the value. Error. 0 prefix must be added to X value. For example, 0CH. If you define any characters, you need to prefix with the zeros. Then only this will be considered as a value. Otherwise, it will take it as a variable. Emulate this. Run. Check for output. FF as A, FF as B. Sum here is FE and carry here is 1. Now check the manual calculation. Sum here is FE, carry here is 0, 1. I hope the concept is clear to you. Now I change the value for A as 30. Value for B as 10. Check the output. What is the carry? What is the sum? A is 30, B is 10, sum here is 40, carry here is 0. This is the concept. I hope the concept is clear to you. We will discuss the remaining concepts on next video. Thanks for watching.